let's take a look at changing basis. So let's look at an example first before we delve into the theory. Suppose I have a vector space V that's two-dimensional, and I have two bases for V. So let's call it B is the basis B1, B2, and C is the basis C1, C2. Suppose I also know some relationship between the two bases. So suppose I know that B1 is 4C1 plus C2, and B2 is minus 6C1 plus C2. Consider this vector x that's in V, and it's 3b1 plus b2. Let's try to find the c-coordinate vector of x. So notice, if I ask for the b-coordinate vector of x, that's easy to compute because x is already expressed as a combination of b1 and b2. And I see that the b-coordinate vector is just 3, 1. If I want the c-coordinate vector of x, then I notice that this is the c-coordinate vector of 3b1 plus b2, and the coordinate mapping is a linear map, and so that's 3 times the coordinate vector of b1 plus the coordinate vector of b2. The c-coordinate vector of b1 is just 4, 1, and the c-coordinate vector of b2 is minus 6, 1. That tells me that the c-coordinate vector of x is 3 times 4, 1 plus negative 6, 1. So it's the vector 6, 4. So now let's take a look at this a bit more abstractly. Right? So the c-coordinate vector of x, since the coordinate mapping is a linear map, we said was equal to 3 times the c-coordinate vector of b1 plus the coordinate vector of b2. Now I can write this as a matrix times vector product, where the matrix has columns the c-coordinate vector of b1 and the second column c-coordinate vector of b2 times the vector 3, 1, which happens to be the b-coordinate vector of x. And so this matrix that I have, it's a matrix that changes b-coordinates into c-coordinates. And so this is the change of basis matrix, and it's denoted P, and then underneath it you write the basis you're going from, and then a left arrow and the basis you're going to. Right? So P from B to C. And then we have that the c-coordinate vector of x is just the change of basis matrix times the b-coordinate vector of x. So let's look at the general case now. If I have an n-dimensional vector space V with basis b1 up to bn and another basis c1 up to cn, then there's a unique n by n matrix, we'll denote it the same way, P sub b to c, that has the property that the c-coordinate vector of x is equal to this change of basis matrix times the b-coordinate vector of x for all vectors x in V. And furthermore, you can give a formula, you can write down what this change of basis matrix looks like. It's the first basis element, so b1, but expressed in c-coordinates. And the second column is the c-coordinates for b2, and so on until you get to the c-coordinates for bn. So here's the picture. We have this abstract vector space V. We have a basis B and a basis C, which gives us two coordinate mappings, both of them to different copies of Rn. And then we can view this map that translates from one copy of Rn to the other as multiplication by some matrix, and that matrix is the change of basis matrix. So how do you compute a change of basis matrix? Well, if you're dealing with vectors in Rn, then it's going to be reduced to row reduction. Right? So suppose I have two bases of Rn, b1 up to bn and c1 up to cn, and I want to compute a change of basis matrix. So what I'm going to do is stack the vectors c1 up to cn, and then stack the vectors b1 up to bn, and then row reduce. The fact that c forms a basis tells me that when I row reduce, I'm going to get the identity matrix here on the left, and the matrix I end up with on the right is the change of coordinates matrix from B to C. And if you want to go the other way, you can either switch the roles of the column vectors and row reduce again, or Note that the change of coordinates matrix from C to B is just the inverse of the change of basis matrix from B to C. Now for general vector spaces, you have a choice. What you do is going to depend on the setup of the problem, whichever way is easier. One, you could fix an auxiliary basis, right? Like, so we've looked at the standard basis for polynomial spaces and things like that. You just pick an auxiliary basis and then use the method from before on the coordinate vectors for the spaces you're considering. Alternatively, you can always just go back to the theorem, which gives you the change of coordinates matrix in terms of coordinate vectors. Let's take a look at some examples. Suppose D is a basis for a three-dimensional space, D1, D2, D3, and F is this other basis for that same space, F1, F2, F3. Suppose you're given that F1 is 2D1 minus D2 plus D3, F2 is 3D2 plus D3, and F3 is minus 3D1 plus 2D3. Let's first find a change of coordinates matrix from F to D. Well, according to the theorem, it's going to have columns F1 in D coordinates, F2 in D coordinates, F3 in D coordinates. So I just compute F1 in D coordinates. I need to just read off the coefficients that are used as weights on the basis D1, D2, D3 when I write out what F1 is equal to. And I see that it's 2 minus 1, 1. I do the same thing for F2, and I need 0 times D1, so that's the coefficient 0 here, and then plus 3 times D2 plus 1 times D3, so that's a 0, 3, 1. And finally, for F3, I need negative 3 times D1, 0 plus 0 times D2, plus 2 times D3, so that's a minus 3, 0, 2. Which tells me the change of coordinates matrix is this matrix shown here. Now suppose you're given a vector x. It's f1 minus 2f2 plus 2f3, and you want to find the d-coordinate vector of x. Well, the f-coordinate vector of x is easy enough to write down. Just try reading off the coefficients again. So the f-coordinate vector of x is 1 minus 2, 2. The d-coordinate vector of x is just the change of basis matrix times the f-coordinate vector. And from the previous page, the previous computation, the change of coordinates matrix is this one shown here, and I'm going to multiply by this vector 1, negative 2, 2, and get that the d-coordinate vector of x is minus 4, minus 7, 3. Let's do an example in R2. Suppose I'm given a basis B, which is the vectors 7, 5, and minus 3, 1, and the basis C, which is 1, minus 5, and minus 2, 2. Let's compute the change of coordinates matrix both from B to C and also from C to B. So let me just pick one. I'll go from B to C, which means I write down the C vectors on the left and the B vectors on the right and construct this big matrix. And then I'm going to row reduce. When I go through the steps of the row reduction, I push it all the way to reduced echelon form. I end up with the identity matrix here on the left, and on the right I have this minus 3, 1, minus 5, 2 matrix, and that's exactly the change of coordinates matrix, P from B to C. Now if I want to go the other way, well, one way I can do this is just to try to invert this change of coordinates matrix from B to C. So I'm going to use that formula we have for inverting 2 by 2 matrices, which means I need to compute the determinant. The determinant of a 2 by 2 matrix is AD minus BC. I compute that to get a minus 1. And so the change of coordinates matrix from C to B is the inverse of the change of coordinates matrix from B to C. So it's 1 over the determinant, so 1 over minus 1. I'm going to swap the diagonal entries and multiply the off diagonals by minus 1. and then I push the scalar inside. And so then I get the change of basis matrix from C to B is -2, 1, -5, 3.